To continue lecturing on here, and we're going to talk more about chapter 15 that we finally got into. So chapter 15, we really started talking about KSP, and remember that KSP is the solubility product. It is a equilibrium constant that is essentially for things that are considered insoluble. So if you think about sort of your solubility rules, these are guys that are typically insoluble. And that means that usually this type of equilibrium is set up in a special sort of way in the sense of how the equations are written. We always have solids on the reactant side, and they always go to aqueous ions on the product side. So because of this, when we do write the equilibrium expression or the KSP expression, it is always usually just the product side, as the reactant side is usually our solid. Do everything the same, so we still square it if there's a coefficient, or cube it if there's a coefficient. We talked about kind of two problems that we type of problems. One does sort of require you to do an ice table. The other one you do an ice table, but it can be very helpful to do an ice table to kind of make sure you don't mess up on the calculations. So if you are just given pretty much the KSP, that should definitely be an ice table situation. When we do our ice table, it is a little bit different as well. So I think we looked at, say, silver chloride there to finish it out last time. You have some equilibrium like this. And initially here we have zeros of these guys. We oftentimes will use a different sort of letter when we're dealing with solubility, and that letter is S. So this would be plus S and plus S. And again, the S here is the molar solubility, which is basically the molarity, which is our moles per liter. And then equilibrium, obviously, we would carry this guy down, S and S. This would go into our KSP expression. We would solve for X, S. And when we do solve for S, that would really give us the molar solubility of the ionic compound altogether. And again, it will also, in a lot of cases, allow us to figure out what is the concentration of the ions that are floating around in that solution as well. The other type of solubility that we sometimes look at is solubility in grams per liter. So a reminder that as you kind of go back and forth between those two types of solubility, it is the molar mass from the periodic table that allows you to do that conversion to go from grams per liters to moles per liter, or vice versa, obviously going backwards. The other type of sort of KSP problem is you're given the solubility of the compound, and you may be given the molar solubility, you may be given the solubility in grams per liter or some other type of unit. But eventually, whatever unit of solubility you're given for the compound, you do want to get it perhaps to grams per liter and then to molar solubility. And once for molar solubility, you really can go into the KSP expression and you could solve for the KSP. You could also do an ice table like we did, I think, on the very first example. That will sort of allow you to understand that you should say multiply and also say cube it, I think was that example we did at the very beginning. It's a very common mistake sometimes people will make, especially if there happens to be coefficients, which there obviously is not in this example. But if there happens to be coefficients and you do have some of those coefficients, sometimes people go, well, coefficient like 2s, still need a square. Table approach for this one, where you're looking to solve for the KSP. These things are typically insoluble. Even things that are insoluble based on solubility rules will have some degree of solubility, even if it's very, very small. And that's typically what we see with these KSP values. They are really small values, which means that for the most part, they do stay at the reactant side and stay together as a solid. But again, even a small amount of it will break apart into ions, so you will get some of that solubility that will occur. Any questions on any of that stuff there that we got into last time? Okay, so I think we did the silver chloride example to finish up on last time. So why don't you do this one? What is the concentration of aluminum? And again, I'm not sure why the dramatic pause there. Aluminum 3+ ions in this saturated solution of aluminum hydroxide. The KSP there is given to you. So take a few moments here, figure out the concentration, and moles per liter will be sufficient. Look, so here we do have the KSP value, and that's pretty much it. Again, you may have to look some of these values up in tables. So we'll start with our dissociation here of our aluminum hydroxide. We do know it's a solid, since I do see a KSP value associated with it. So that's going to give us aluminum. It will give us 3 hydroxides here. Our KSP expression in this case then would be aluminum times hydroxide. And once again, we do need a cubit in this case because of the 3 that we see here. And that would equal 2 times 10 to the minus 32. Doing our ice table, we'll go with 0 and 0. We'll go with our change, which will be plus S plus, once again, 3S. You don't want to miss the 3 there either. This will then get us S and 3S at this point. Any questions on the ice table here? Like normal, we're now going to put this into our KSP expression. And if we do that, that gets us an S times a 3S that is cubed, and that will equal 2 times 10 to the minus 32. I believe that will give us a 27S to the 4th. Do not forget to also cube the number, which is a common mistake people overlook. They oftentimes get the letter, but not so much the number, as obviously is 3 times 3 times 3 times equals 2 times 10 to the minus 32. We're going to divide our 27 to the other side. And if we do that, we will end up with here like 7.407 times 10 to the minus 34. We want to take the 4th root at this point, right? So 4th root of both sides. On your calculator, if you're not sure, you can do that by taking the number, hitting like your caret button if you don't have a button, and do a parentheses 1 divided by 4. We'll take the 4th root of it. If you don't have the actual dedicated sort of button you can do that with. If you don't have perhaps, a button that looks like that, you could do that. And that would get us, not that, let me try that again. Let me go. Let me hit the right button here. There we go. All right, looks like you got an S of like 5.2 times 10 to the minus 9. Again, your calculator might have run out of room, and you might just have a bunch of zeros and a 5 at the end if you're in decimal form. That is our molar solubility. If we go here to aluminum, that would be the concentration of aluminum, right? Would be in this case 5.2 times 10 to the minus 9 molar, which is what that would be. We could also, if we wanted to, right, get the concentration of hydroxide. Hydroxide, those concentration would be 3 times S, right? So take 3 times the 5.2 times 10 to the minus 9. And that would get us something like 1.6 to the minus 8 molar. Yes. Yeah, you could have went with 5 because that really was kind of the only number there. So yeah, and then you could round that up to 2 if you wanted to. Yeah. Other questions on that? Yeah. Would you substitute, I'm sorry, the KSP into the I'm not sure I understand. I'm sorry. Plug it in to check it. Is that what you're asking? You could, yeah, ideally. Ideally, it hopefully should be about the same again here. We did a little bit of rounding, obviously, here. So if we did that, you know, you get about 2. I get 1.99 to the minus 32 if you plug it back in. So it's pretty close with the rounding. Yeah. So yeah, you could definitely check yourself if you wanted to by putting it back into there. Other questions? Okay. All right. So let's talk a little bit about using KSP values and to help us determine solubility, maybe which thing is more soluble, which one is least soluble, and in general, can you use the solubility KSP values to help you determine that? And the answer is yes. In certain situations, you can directly use the KSP values to help you determine what ionic sort of solid should be more soluble than another. And the only place where you can directly use the KSP to compare those things are situations where they do break apart into the same number of ions. So you only way you can compare them is if they break apart there into the same number of ions, like 2 ions, 3 ions, or so forth. So if we looked at something like AgI, CuI, and calcium sulfate here, each of those guys, when they break apart, will break apart into the same number of ions, not actually the same ions, but the same number of ions. So obviously we have 2 ions here. For our copper 1 iodide, we would have a copper ion. It's not +2. We would have a copper ion that's +1, and an iodide, which is also 2. And for our calcium sulfate here, we would get basically a calcium ion and a sulfate ion here, which also is 2. So because basically these guys break apart into the same number of ions, you can go to the KSP table, you can look at the KSP values, and you can use it to determine which one would be more soluble. And that is the one that has the larger KSP value would be more soluble. That's because the larger KSP value is really just a large K value. And when we have a large K value, that means that we should pretty much have products at equilibrium. And always in these reactions, as we talked about, solids on the left and aqueous soluble ions are on the right-hand side. So the larger the KSP value, even though it may be a really small number in comparison to another one, would be more soluble because you should have more products sort of happening there. So if you got the same number of ions and you want to kind of make a prediction like which one would maybe stay in solution longer or come out of solution earlier, you could use KSP values to help you do that. It is supposed to be an and. Thank you. So larger the K value, more soluble. The smaller the KSP value, the least soluble it would be. Now, if you're trying to compare salts that actually do not break apart into the same number of ions, you really cannot use the KSP values to help you determine that. For example, if we were to compare these 3 here, this guy would break apart into 2 ions, this guy would break apart into 3 ions, and this guy would break apart into like 5 ions right here. So in this particular case, if we tried to use the KSP values to help us determine which one should be more soluble versus another, we would actually choose the top guy as being more soluble based off of the KSP values. And this guy would be the least soluble, right? Based once again off of our KSP values that we could look up. But when you actually do the calculation like we just did in the previous problem, the molar solubility, we actually see the opposite trend here. It is actually this guy here that is more soluble. And actually the guy that had the larger KSP value is actually the least soluble in this bunch. So in a situation where you're comparing guys that have different numbers of ions, you cannot directly go by the KSP value. You actually have to do the calculation and then compare which one would be more soluble or not. But if you do have ones like the previous slide where it is the same number of ions, you're good to go. You can kind of look at the KSP value and have an idea as to which one should precipitate out first. Any questions on that there? So again, you have to calculate it if you have different numbers of ions in them. All right, so let's talk about some things that will affect the solubility of a compound. And one thing that will affect the solubility of a compound is the common ion effect. And obviously, we talked a lot about the common ion effect when we were talking about buffers. And if you remember, the presence of a common ion in a sort of acid-base situation will cause the weak acid or weak base to basically stay together and not really break apart as much. And a similar sort of idea happens here when we talk about solubility. Because of the presence of a common ion, it will decrease the solubility of a salt. So why is that? Again, if you just look at the generic way that these reactions are written, again, we have solids on the left-hand side of the arrow. We have our aqueous ions on the right-hand side of the arrow, which means if we have a common ion in a situation like this, the only place it should show up would be on the right-hand side of the arrow, right? Which means essentially we are adding more of an ion on the right-hand side. And Le Chatelier's principle would then say the equilibrium should shift away from that side, right? Which would then put it back to the solid side and decrease the solubility. So kind of the same idea as what we saw with our weak acid or weak base when it broke apart. It shifts the equilibrium back to it staying together. Here, it's basically going to shift equilibrium back to the solid side of the reaction and going to keep that solid together. The result of that, obviously, is less of it will break apart into ions, and the solubility would come down. Any questions on that there? Okay, so let's take a look at an example like silver bromide. Let's first look at what the solubility of silver bromide would be in water. So to do that, we have the KSP value that's just hanging out here. I'm going to go with that for silver bromide. So we will do our table. So we'll take our silver bromide. It will break apart, obviously, into a silver ion and a bromide ion. And our KSP, obviously, in this case, would be the concentration of silver times the concentration of bromide. And once again, here, that will equal our 7.7 times 10 to the minus 13. Doing our ice table, we have 0 and 0. Change would be plus S. And at equilibrium here, we will have S and S. This will go into our KSP expression, and that will basically give us S squared is equal to 7.7 times 10 to the minus 13. We're going to take the square root of that there, and that is going to give us 7.7 to the minus 13. To give us an S of, we'll call it here, 8.8 times 10 to the minus 7 molar, right? Which, if we wanted to figure out the solubility of it in grams per liter, we could use our molar mass, silver, which is 107 point, what we got there, 9. And our bromine, which is 7990. So if we add that together there, we will end up with 107 point, oh, that's not it, 107.9 plus a 7990. And that will give us 187.8 grams per mole. And just for purposes here, that would tell us that we would have moles per liter times our 187.8 grams per mole. That's going to give us a solubility of this guy of 1.7 times 10 to the minus 4 grams per liter. Yeah, so that is the solubility that we got going on here. Any questions on that calculation? That is not very much, right? So it's like 0.0002 grams per 1,000 milliliters of water. So what happens though if we have the same silver bromide, but it's in sodium bromide, a solution of sodium bromide? So let's take a look at this here. So we would still have our same silver bromide here that will set up our equilibrium. And we do have, though, some sodium bromide present. And obviously, sodium bromide will break apart as it is soluble. And basically will be a sodium ion and a bromide ion floating around in that solution. And it is obviously, hopefully you can recognize it is the bromide ion, right? That is our common ion that we have in common here. And if the concentration of our sodium bromide is 0.001, it is a one-to-one relationship between the sodium and that, and it's also a one-to-one relationship between the bromide and that. And again, where this is important is this would be 0, but we would have, again, that initial concentration of the bromide coming in really from our sodium bromide in this particular case. The change part here would be plus S and plus S, which means at equilibrium here, we would have S and 0.001 plus S in this case. Any questions on that there? That is going to go into our expression, and that would get us basically S times 0.001 plus S equals our 7.7 times 10 to the minus 13. That is definitely a small value of K. So just like we've done previously, we can actually assume in this case that S is going to equal 0 because of the small value of KSP in this case. Clearly, like before, we cannot obviously clear out all the S's, otherwise we have nothing to solve for. It again, in this case, is going to be the S we were going to add to a number that we're going to get rid of. And if we do that, that reduces this down to S times 0.001 equals 7.7 times 10 to the minus 13. Obviously, in this case, we're going to divide the 0.001 to the other side. And that would get us 7.7 to the minus 13 divided by 0.001. And that would get us a molar solubility here of 7.7 times 10 to the minus 10 molar in this particular case. And if we took that 7.7 times 10 to the minus 10 moles per liter and multiplied it by the molar mass there of our 187.8 grams per mole, will get us some of this here, maybe. That would get us here times 187.8. Helps it times it by the actual number would work. There we go. Gives us something like 1.5 times 10 to the minus 7 grams per liter, if I am not mistaken, in that case. First off, any questions on that calculation? We should also check it, and it is going to be okay if you take 7.7 times 10 to the minus 10 and you divide it by 0.001 and times it by 100, you're nowhere near even 1%. So the assumption is good. You should obviously still check it. In most cases, in this situation, because the KSP is really small, you usually will be okay on your assumption, but you should still probably give it a check. In terms of comparing the solubility of silver bromide in water versus silver bromide with the common ion, which one is it more soluble in? It is more soluble in water, yes. You could dissolve basically 0.0002 grams in 1,000 milliliters versus in the common ion, you could dissolve basically 0.00000002 grams in 1,000 milliliters of water. So it is more soluble, obviously, here in the water. The reason, obviously, is because of what we talked about. Because of that common ion, it is going to push the equilibrium back this way, keeping this guy still together. And that is obviously reflected in either comparison of the molar solubility on both sides or the solubility in grams per liter. Any questions on any of that there? Okay, so why don't you try one here? The KSP for silver chromate is 9 times 10 to minus 12. What would be the solubility of this compound in a solution that has 0.1 molar potassium chromate? And why don't we do both solubilities? Why don't we do molar solubility and solubility in grams per liter? And I'll give you some numbers. Silver, as we were just using, is 107.9. What else we got there? Chromium is 52. And oxygen is 16. All right, so take a couple moments here, calculate the molar solubility and also the solubility in grams per liter. Look, so once again, obviously we have a KSP, so might as well just start with our equation here, which is our silver chromate. We'll break apart into a couple of silver ions and a chromate here. That's going to give us a KSP that will look something like silver squared because of the coefficient times our chromate. And obviously that would equal our KSP value there of 9 times 10 to the minus 12. Going into our ice table here, we do want to also realize that we do have it in a solution of potassium chromate, and potassium chromate would be K2CrO4. That is going to be soluble because it's attached to potassium, which is soluble in everything. That means it will break apart into a couple of potassiums and a chromate ion in this case. And once again, in this particular case, it is the chromate ion that is the common ion that we would see. That's really important when we do our ice table because that should be 0, but we should then have an initial concentration that is coming from the potassium chromate for the chromate part. That's what's going to hopefully kind of push it the other way. Rest of it will be kind of like normal. Once again, we do have a 2 there, so we don't want to forget it as 2s. This would be plus s. Coming down this way here, we would end up with 2s and 0.1 plus s. Any questions on the table there? Yeah. Do you estimate 2 separate ice tables? Is that what you're asking? One for the potassium chromate, is that what you're asking? Yeah. And the other? No, because this is a strong electrolyte because it's soluble. It's a solution, so it will 100% break apart. It won't set up an equilibrium. So really the only thing that will set up an equilibrium is the silver chromate in this case. Yeah. Other questions? Okay, so since we have that, we will then put that into our KSP expression here, which would get us 2s. That's going to be squared. and that's going to be times our 0.1 plus S, which will equal our KSP of 9 times 10 to the minus 12. Once again here, that obviously is a small value of K, so why not assume that S is equal to 0? We're not going to get a ton of it coming apart, probably even less now that we have this common ion there pushing it back the other way. That would then reduce this down. I'll just do the math there. 4S squared times 0.1 is equal to 9 times 10 to the minus 12. However you want to do the math here, you could do it separately, or you can multiply them together, the 4 and the 0.1 if you like. That gives you 0.4 S squared is equal to 9 times 10 to the minus 12. Obviously, we're going to divide that and also then take the square root of it. So if we divide it first, 9 to the minus 12 divided by 0.4, then take a little square root action on it. Going to get us an S value here of, we'll call it 4.7 times 10. Too many zeros. 1, 2, 3, 4, 5, 6, minus 6. And this would be our molar solubility in this case of the silver chromate, which means that that would be one of the answers, right? The other answer, since we're also looking for, again, are grams per liter, we'll use our molar mass from the periodic table here to calculate that. So 107.9 plus a 52 for the chromium. And we actually have 4 oxygens, so 4 times 16 gives us a molar mass of 223.9 grams per mole. So taking our 4.7 times 10 to the minus 6 moles per liter of silver chromate. Yes, sir. Is it? It is. Thank you very much. 107.9 times 2 would be better. Plus 52 plus 4 times 16. So we actually should have, thank you, 331 here. So there we go. 331.8. Thank you. And we will then use our molar mass that's now correct. So that's good. 331.8 grams per mole. Obviously, those guys will cancel, and we will end up with 4.7 to the minus 6 times that. Will get us something like 0.0016 grams per liter, basically. It's the solubility of that in grams per liter. We also should check our assumption here. And again, you're going to be okay. So 4.7 to the minus 6 divided by 0.1 times it by 100 is like 0.004%. So, you know, the check is good here when we did it. Couple other things. Obviously, if I wanted the concentration of silver at this point, I would need to do 2 times the 4.7 times 10 to the minus 6, right? And if I wanted the concentration of chromate at equilibrium, right, I would do 0.1 plus this number, which essentially will get me 0.1 at that point. And again, so there are some variable type stuff that you can solve for, obviously, at the end of this road. Once again, also a reminder that pretty much when you do solve for that S, that is really the molar solubility of this entire compound. Any questions on that there? So as we can see here, we didn't calculate it in just water, but typically speaking, the presence of that common ion will cause, again, that shift in equilibrium based on Le Chatelier's principle and cause it, again, to shift back this way, really keeping the solid there together. All right, so that is common ion and its effect on solubility. Let's also talk about another thing that can affect solubility, which is pH. And pH has a really big effect on the solubility of salts that are either acidic or basic types of salts. And the presence of a common ion, as we just saw, will decrease the solubility. The insoluble bases, if you have an insoluble base, it is typically will dissolve in acidic solutions. And if you have an insoluble acid, it typically would dissolve in basic solutions. So we're going to talk about why that is here. So we'll take a look at this example, which is an insoluble base, which is magnesium hydroxide. When it breaks apart there, that is what we get, a magnesium ion and a hydroxide ion. So if we did our KSP for this, our KSP here would be the concentration of magnesium times the concentration of hydroxide. And again, a reminder, we do need to square it because of the 2 that we see there. And that would equal our 1.2 times 10 to the minus 11. So if we ran through our sort of ice table here and to figure out the molar solubility of everybody, let us do that real quick. So what we will do is, I'll actually get rid of that so I have a little bit more room. We will go through our ice table here, which would be 0 and 0. Change would be plus S and plus 2S. And that means at equilibrium, we would have S and 2S. Putting that into our KSP expression would give us S times 2S. And we do again need to square it because of the coefficient. Would equal 1.2 times 10 to the minus 11. Cleaning up the left-hand side and remembering to also square the number here, that gives us something maybe like 4s cubed is equal to 1.2 times 10 to the minus 11. At this point, we're going to divide the 4 to the other side and take the cubed root of our answer. So 1.2 to the minus 11 divided by 4. Basically gets us S cubed is equal to 3 times 10 to the minus 12. Once again, taking the cubed root at this point. Where's my button there? Will get us an S value of like 1.4 times 10, 1, 2, 3, 4 to the minus 4 in this particular case. Any questions on that there? So this would be our S value, which would be the concentration here of magnesium. But if we're talking about pH, the more important guy would be the hydroxide, right? And to get the actual hydroxide concentration at equilibrium, it is equal to 2 times S here, which means that to calculate the hydroxide concentration, that would be 2 times S, which would be 2 times our 1.4 times 10 to the minus 4. And that is going to get us 2.8 times 10 to the minus 4 molar. Because I have the hydroxide concentration, I could actually calculate the POH in this case, right? And the POH would be minus the log of 2.8 times 10 to the minus 4. And if I do that, we will end up with, we'll call it POH of 355. And that means that my pH here would be 14 minus 350. Come on, 5. There we go. Minus 14. That will give me like a 10.45 in terms of my pH in this case. So first off, I was able to, in this particular case, because there's hydroxide, or if there happened to be H3O plus or H plus, I could actually calculate the baseline pH of this solution, which is 10.45, which is not bad because this is a base, so that's pretty good, right? So that's 10.45 in this particular case. So why is that number important? So let's talk about what would happen if we had this solution and we decided to sort of play with the pH. So if I took the pH below 10.45. What would happen? Would it become less soluble or more soluble? Would it stay the same? What do we think? Well, let's talk through it then. How can I lower the pH? Should I add an acid or a base to lower the pH? That is a good answer. So when we add an acid, right, we're essentially adding H plus. Yes. So what happens when I add H plus to this equilibrium? Anything? H plus, will it be attracted to anybody in this equilibrium? It would make water, yeah. So it would be attracted to the hydroxide, right? The hydroxide and the additional H plus would be, as you said, making water in this case, right? The result of making water will do what to the hydroxide concentration? Increase it, decrease it, will it stay the same? It will decrease it, which means it's like removing hydroxide, right? And our good friend Le Chatelier's principle will say the equilibrium should shift which way? Should shift towards it, yes? And because you're removing hydroxide in this case, because you're adding an acid, you are basically removing the hydroxide. It will cause the equilibrium to shift to the product side. And on the product side, would that increase the solubility or decrease it? What things are on the product side here? Solids or aqueous things? Aqueous things. So that should increase the solubility, right? It's going to cause equilibrium to shift away from the solid to the side where we have aqueous ions. And we would see a shift in the equilibrium to the right in this case, causing an increase in the solubility, right? And that's what it means when it says in that sentence that if you have an insoluble base like what we have here, it will dissolve in acidic solutions because you have added more H plus. You're going to get rid of the hydroxide, going to cause the solid to shift away from it, or the equilibrium to shift away from the solid to kind of fill that hole that you made by removing the hydroxide. Any questions on that? Do I need to get it totally acidic for this to happen? I do not. I need to just drop the pH below 10.45 and you will start to see it dissolve, which could still be basic, right? So just lowering the pH doesn't necessarily have to be acidic at this point to see that happen. Clearly, if you got to acidic pH, a lot more of it would dissolve, right? But you will start to see it to dissolve once you get below that 10.45 in this particular example, which is why this number is important. It gives us sort of a baseline of where we would start to see some movement perhaps in the solubility of it. And again, you don't necessarily even have to get it down to acidic pH to actually see a pretty good jump in the solubility. Just dropping a little bit will cause a good amount of it probably to dissolve. Now, what would happen if I did the opposite here and I decided that I wanted to increase the pH above 10.45? When I increase the pH above 10.45, what will happen in this situation? Will it become more soluble, less soluble? Will it stay the same? So let's talk about how do I raise the pH? I need to add an acid or a base. I need to add a base, right? Which means that you're essentially adding hydroxide, right? We do actually see hydroxide here, right? It's on the product side, which means in this situation, when we increase the pH, we are actually adding more hydroxide. That's going to cause the equilibrium to shift which way? It's going to cause it to shift to the left towards the solid, which means the solubility should start to decrease in this case, right? So again, here, going to cause the equilibrium here to shift to the left, causing the solubility obviously to decrease. So in this particular case, if you brought the pH above 10.45, you would actually see more solid being formed. I don't know if you can visually maybe see it, but technically more solid would be formed at that point. It would really keep it obviously in solution. So pH plays a really big role in terms of, especially when you're dealing with things that are acidic or basic, as to whether or not you might see a solid form or not form, depending on the pH. We don't really do these experiments at all anymore, qualitative analysis experiments, but experiments we used to do, which were qualitative analysis experiments, which is about like really KSP, which is to try to keep things in solution and selectively precipitate out ions. A lot of the steps that you do in those type of experiments are you play with the pH. So you like make it acidic, then you make it basic, you make it acidic. And the purpose of that is it allows certain ions to stay in solution while you can take out other ones as solids. And by changing the pH around, it plays a lot with the solubility. So obviously the same effects would occur if we were starting with an insoluble acid. If you brought it into a basic solution, because the insoluble acid would have H plus on the product side, and you added a base, you would make water, which would give you kind of the same effect, and that would increase the solubility of it, and vice versa, obviously going the opposite way. Any questions on pH here? Okay. All right, so we talked a little bit about at the very beginning as to whether or not a solid would form, and we can look at the Q value versus the KSP value, and a reminder that if the Q is greater than the KSP value, then we will see a precipitate form, and if Q is less than the KSP value, we will not see a precipitate form. Also a reminder that we calculate Q the same as KSP, right? So it's really the same thing. You still take the coefficients as your exponents. So let's take a look at one here. And what we want to know is if we take 2 milliliters of a 0.2 molar sodium hydroxide solution and we add it to 1 liter of calcium chloride, will a precipitate form? So a couple of things here that you want to look at is there any combination of ions that will actually, perhaps based on solubility rules, make a solid? So in this case, the sodium hydroxide is a source of 2 ions, is a source of sodium ions and hydroxide ions, right? And the calcium chloride is a source of calcium ions and chloride ions, right? So basically what we want to know is there any combination when these guys basically switch partners in this double displacement reaction, will any of them make a solid? And hopefully from your solubility rules, there is only one option, which would be basically these guys could come together. Obviously sodium is soluble in everything. So sodium chloride obviously would be soluble. You wouldn't expect a solid to form. So with that, what we want to know is Q greater than the KSP for calcium hydroxide? And the KSP that you can find in the table is 8 times 10 to the minus 6. So I'll let you pick it up from that point, calculate Q, and see will a solid form in this case. Okay, let's take a look. So we do obviously want to calculate Q. It is based off of obviously our calcium hydroxide here. And that would break apart into calcium ion and a couple of hydroxide ions here. That would give us really a Q that is the same as our KSP in terms of how we're going to calculate it. The important part here is we do need the concentrations of these guys when they are mixed together. So we want to make sure that we have the proper concentrations. Clearly, we're going to take some sodium hydroxide and we're going to take some calcium chloride and we're going to toss them together here in a mixture. So their concentrations will change once they get together. So we got to get it in that mixture. The sodium hydroxide is the source of hydroxide in this case. And that means that the concentration of hydroxide, when we toss it together, you could do a little M1V1 equals M2V2 action. In this case, hydroxide, we have 2 milliliters. times the concentration of the hydroxide. And I'm going to divide it by the total volume in this case. I'm going to convert my 1 liter into 1,000 milliliters. So I'm just in milliliters for everybody in terms of the volume. So 1,000 milliliters of our calcium chloride and 2 milliliters of that guy gives us a total volume of 102 milliliters. That way everything cancels out correctly here. We end up with 2 times 0.2 divided by 1,002. Gets us a concentration of hydroxide of 3.99 times 10 to the minus 4 molar. Any questions on that there? We also want to get the proper concentration of calcium, which would come from our calcium chloride in this case. And we want to do the same deal. Our calcium here would be, again, I'm going to use milliliters. So 1,000 milliliters are a liter times the concentration, which is 0.1 molar, divided by, again, our total volume of 102 milliliters. Gives us 1,000 times 0.1 divided by 1,002. Will give us 9.98 times 10 to the minus 2 molar. Now that we have our proper concentrations here, we can take these into our Q expression. So our Q would then equal our calcium, which is 9.98 times 10 to the minus 2, times our hydroxide, which is 3.99 times 10 to the minus 4, and we're going to square it. That's going to get us 3.99 to the minus 4 squared. Maybe not, try that again, 3.99 to the minus 4 squared. There you go. Times 9.98 to the minus 2, going to give us a 1.6 times 10 to the minus 8 as our Q value. Any questions on that? Here I do need to square it, but I do not need to multiply it by 2 because that is the concentration of hydroxide already at the end. So we didn't need to do a nice table, so we don't have to multiply that by 2. In this case, we want to compare our Q to our KSP, and Q is less than greater than KSP. Q is less than the KSP. Will we see a precipitate in this case? We will not. It kind of goes the opposite way towards product side, right? Which means no precipitate will form. So this illustrates another really important point that we've been talking about, in addition to, say, something like common ion. Something like pH, the actual concentration of the ions that are floating around in a solution are important as to whether or not you'll see the solid form or not. In this case, even though solubility rules tell us we should see a solid, because the concentration of the ions are not what we need it to be, we actually will not see the concentration, we will not see that solid form. 100% always in that situation, what you would see, the conditions that are there are really important as to whether or not you actually do see, again, something come out as a solid or not. Question on that there. All right. Let's talk about one last sort of aspect of KSP, which can be really helpful. And that is the idea of, and like I said, we actually don't do these experiments anymore here, but there's a whole set of experiments that usually go with sort of this type of class, which are what are referred to as qualitative analysis experiments. And the idea of qualitative analysis experiments is you basically have a solution with a bunch of ions floating around. They actually could be negative as well, but we'll go with positive ions floating around. And the goal of these experiments are to selectively precipitate out one ion out of the solution as a solid, while leaving everybody else kind of floating around still in the solution. Now, why would you want to sort of selectively precipitate out one ion versus another? Why not just add something where everybody comes out, together and it's all good? One of the reasons why you wouldn't want to do that, for example, is if we had a solution, like in this problem, that contained bromide ions floating around and chloride ions floating around, you could add something that contains silver to this. And based on solubility rules, chlorides, bromides, iodides, they are soluble in everything except silver, lead 2, and mercury. So in this case, this would cause a precipitation to occur. The problem is both of those guys, when silver bromide precipitates and silver chloride precipitates, they're essentially white solids, which is what these pictures look like. They're basically kind of the same looking sort of solid. So if you wanted to take out, say, silver chloride versus silver bromide, and you just randomly added silver to it, you would have no way to go. I think this white solid is the silver chloride. I think this white solid is the silver bromide. There would be no way for you to really know which one you took out of the solution, which one might still be in the solution. So you could actually use KSP to help you know, how much silver should you add to get one to precipitate out and maybe leave the other one in solution still. And the purpose of sort of selective precipitation is this: you can selectively precipitate out one ion from solution, and then when you stop seeing a precipitate at that point, you can know I pretty much got rid of all that ion out of the solution. You then can actually change the concentration of your precipitating reagent, and you will then see perhaps the next guy start to precipitate out, and you could go, I know for sure that is the other ion that's coming out of solution. So you could kind of control what would come out of solution by knowing these things. So in this particular problem, we want to add silver to only take out silver bromide as a solid, but still leave my chloride still floating around in the solution, basically as an ion. So to do that, we want to look at the two KSP sort of reactions that will occur. So again, obviously we could form silver bromide that will set up an equilibrium and form silver ions and bromide ions. The KSP is what we saw a little bit earlier at 7.7 times 10 to minus 13. We also could do the same thing with our silver chloride, which will set up silver ions and chloride ions with a KSP of 1.6 times 10 to the minus 10. So how can we use this idea here to help us? Well, we do know the concentration of each of these ions, and each of these ions are floating around with a concentration of 0.02 molar. So if we wrote the KSP expression first for silver bromide, it would be the concentration of silver times the concentration of bromide would equal 7.7 times 10 to the minus 13. I am interested in this question as to how much silver I need to add. So if I solve for the concentration of silver, it would equal 7.7 times 10 to the minus 13 divided by the concentration of my bromide ions, which I luckily know is 0.02. So if I go 7.7 times 10 to the minus 13 divided by 0.02, that will give me we'll try again. 7.7. All the wrong buttons today. 0.02. There we go. Well, that will give us 3.9 times 10 to the minus 11 molar. So what does this number represent? This number represents the concentration of silver that you need to start to see what happened if you get it to this concentration. You will then start to see silver and bromide come together as a solid. So this is the minimum concentration in this example of silver that is needed to precipitate silver bromide, right? So that is basically what that number represents. We can also look at silver chloride and see what type of silver concentration we need to get silver chloride to come out. And we would do a similar calculation. We would take our KSP expression, times it by silver times chloride, and that would equal 1.6 times 10 to the minus 10. Solving again for the concentration of silver that is needed to precipitate out silver chloride. We'll take our KSP divided by the concentration of our chloride, which again, we do know in this example is 0.02. And if we do that there, 1.6 to the minus 10 divided by 0.02, we would need something like 8.0 times 10 to the minus 9 molar. And that represents the minimum amount of silver that you would need to start to see silver chloride come out of solution. So that's the minimum silver concentration needed to precipitate out silver chloride. So in this example, we want to keep the silver chloride still, or the chloride still floating around in the solution. So if we 11 molar, but we keep the concentration of silver less than 8.0 times 10 to the minus 9 molar, we'll see silver bromide start to come out. So as soon as we hit a silver concentration of 3.9 times 10 to the minus 11, we will start to see some solid come out. And if we continue to increase the silver concentration, but keep it less than 8 times 10 to the minus 9, we will still see solid come out, right? And you keep doing that, you can increase it a little bit more if you want. At some point, we will again stop seeing solid come out. At that point, we know that we have hopefully precipitated out all of the silver bromide. And then it would be safe to take the silver concentration to 8 times 10 to the minus 9 or higher. And then we would again start to see some solid come out of that solution. And we could feel very safe to know at that point that solid should be our silver chloride. So by using KSP, we could figure out the minimum concentration, say, of a precipitating reagent that you would need to precipitate out one ion, but still keep another one in solution. And as you can see here, they both are going to be precipitated out by silver, but it's controlling the concentration of that silver that allows you to selectively precipitate out one versus the other. Question on that there. Yeah. You would. So what would happen if I just decided, hey, I'm just going to dump in 8 times 10 to the minus 9 or higher silver? What would happen at that point? Everybody would come out together, right? And then you, I mean, if that's your goal, just to get everybody out, you can, but you would have no way to know which one is like the silver chloride, right? Or which one is the bromide. So you definitely, if you went too high, right, you would get everybody come out once. What would happen if I had the silver concentration lower than 3.9 times 10 to the minus 11? Would I see anything happen? I wouldn't see anything happen, right? Because that's too low for the bromide, and that's still too low, obviously, for the chloride, so you wouldn't see anything to happen. So again, if you want to kind of pick each ion off one at a time, you could kind of, in this example, control that silver concentration, and you'll know what you have coming out at that point. Yeah.
Only precipitating out the bromide.
It would in this example, right? Because if it's less than 8 times 10 to the minus 9, but higher than 3.9 times 10 to the minus 11, that's plenty to get it to precipitate out, right? Yeah. You would, at 8 times 10 to the minus 9, that's where you would start to see silver chloride start to precipitate out. So if you were doing this, what you would do is obviously you would keep the concentration of silver below that 8, and you would just keep adding, right, until you don't see any more solid form when you add some silver, right, at that concentration. And at that point, you're pretty much at the high end for bromide, right? If you're right around that 8 times 10 to the minus 9 or a little less than that, right? You're pretty much at the high end, which means you should definitely see the bromide come out. And if you keep adding that at that concentration, a little bit below that 8 times 10 to the minus 9, you'll see precipitate. You'll see precipitate at some point. You'll stop seeing precipitate. And you could feel good that you probably have now completely removed all of the bromide at that point. And now it's safe to kind of bring the concentration of silver up a little bit more. And then you should hopefully start to see more solid, which you also could feel good about knowing that that definitely should be chloride at that point coming out. Yeah. Other questions? Okay. So you can use, obviously, as we can see here, KSP to selectively precipitate out ions, which is before we move off of this slide, why did they pick, by the way, this silver bromide to come out first? Is that what we would expect to happen if we look at the KSP values? And can we look at the KSP values here to determine which one is more soluble? In this case, we actually can look at the KSP values because silver bromide breaks apart into 2 ions, right? And silver chloride breaks apart into 2 ions, which means when we look at the KSP values, the larger KSP value is which one? It is the silver chloride, which means in a combination of those 2 things, we should expect the silver chloride to be more soluble, which is why we expect the bromide to actually come out first. As you can see from the calculations, that's what would happen in this particular case. All right, so just to finish up on this topic here, those type of experiments that I was talking about earlier, which are qualitative analysis experiments, they're broken apart into groups, these ions, group 1, group 2, 3, 4, and 5. They are not groups from the periodic table, but they are grouped together based on solubility rules. So for example, group 1 is silver, mercury 1, and lead 2, and that's basically your solubility rules for chlorides, bromides, and iodides. Everybody's soluble except for those 3. Then we have group 2, which are these ions here, and group 3, and then group 4, and then group 5. And each of these groups in qualitative analysis has what's referred to as a precipitating reagent. And this is the one that basically will separate out all the groups from each other. So if you had a mixture of all these groups together in a test tube, and these would just be ions floating around in a test tube, you could add hydrochloric acid, which is a source of chloride, and that will take out all the group 1 ions as solids, and everybody else will still be floating around as ions. And then if you wanted to, you could use hydrogen sulfide gas, which is not so great, in really acidic conditions like 0.5 pH, and you could get all those guys come out as sulfides. You could also, for group 3, use hydrosulfide gas, but it is basic conditions. So between group 2 and group 3, although again, they're using the same reagent, which is basically sulfide to precipitate it out, the pH conditions are different. So that, as we were talking about earlier, will allow group 3 reagents, basic ions, to stay in solution because they need basic conditions to come out, while allowing group 2 guys, which need acidic conditions, come out. Then you switch it around. By the time you get down to group 5 or group 4, pretty much there is those guys that are soluble in everything, things like potassium, sodium, ammonium. So a lot of times we rely on like flame tests to try to identify some of these guys, which if you've done flame tests before, they're sometimes hard to do. That is what you look like if you were doing this experiment. Those are flame tests that we've been talking about. All right, so the last little part of this chapter is another part of equilibrium, which was referred to as KF. And that is really the equilibrium constant for complex ions. And a complex ion is a central metal atom that is positively charged. That's positively charged, and it has bonded to it 1 or more molecules or ions. They are sometimes referred to as a ligand, and a ligand is a Lewis base. So if you remember, Lewis bases are things that are electron pair donors. So those are guys that will give away a pair of electrons, typically to a Lewis acid, which is something that will accept a pair of electrons. And that's sort of what goes on with a complex ion. It's sort of a Lewis acid base sort of situation. So in this case, something like cobalt and our chloride ions will come together to make this complex ion that is here. So essentially you have a cobalt in the middle, and attached to it are basically 4 chlorides basically attached. overall chlorides, each of those chlorides are -1, and the cobalt has a +2 charge, which means overall this complex ion has a -2 overall charge, as there's -4 from the chlorides, +2 from the cobalts. We could write an equilibrium constant for this, which is known as the formation constant, and it really is the equilibrium constant for complex ions. And it is just like normal. It is our products over our reactants. So in this case, our cobalt, like so, complex ion over our cobalt and our chlorides. We again do need to take it to the fourth because of the coefficient like normal. Depending on sort of the ligands that are attached, that should be +2 over here. And the complex ion or the metal ion will give some different sort of properties. So these both are cobalts, but depending on what's sort of attached and what's going on there in terms of ligands, we do get some different sort of properties. Now, as the Kf value increases, the stability of the complex ion also increases. And that is because as the Kf value increases, that means that we would have more products, and more products would be our complex ion in this particular case. Now, ligands, they do actually come on one at a time. So the process at which ligands are added to a metal actually occurs basically one at a time, kind of similar to how hydrogens come off. They do come off one at a time. So our ligands will actually come on one at a time. So in this particular case, what would happen is the very first thing that would happen is our cobalt would pick up basically one chloride and would make COCl plus. And you could have an equilibrium constant value for that step. The next step that would happen is this guy here would then pick up another chloride, and that would make our COCl2, which you could have an equilibrium step for. Then our COCl2 would pick up the third chloride, giving us COCl3, and now that would be -1. And lastly, this guy here would pick up its last chloride, gives us COCl4, 2 minus K4. Now, it is a stepwise addition as to how ligands come on. And again, if we were to add up all these reactions together, basically, this guy and this guy would cancel, that guy and that guy would cancel, this guy and that guy would cancel. And that would leave us basically the overall reaction that we see up on top, which is the cobalt gets basically 4 chlorides if you add all those guys together, and we get really our complex ion at the end. By the way, the Kf value, if we did have this information given to us, what do we do with all these K values now that we added these together? We do multiply them, yes? K1 times K2 times K3 times K4, right? So a reminder that when you add together equilibrium reactions, you do multiply the K values together, you don't add them. Yeah. Any questions on that? All right, so let's talk a little bit about some ligands, and we're going to take a whole chapter later on where we talk a lot more about complex ion and coordination compounds and the different ligands that are there. So common ligands, since they do basically donate a pair of electrons, things that are able to donate a pair of electrons are things that are electron rich. And those are things that have negative charges, right? In order for you to become negatively charged, you had to gain some electrons. So things like Cl minus, CN minus, things with negative charges, usually means that they've gained some electrons. Also, polar molecules that have non-bonding electrons also are good ligands. So things like water, which has non-bonding electrons on the oxygen, NH3, which has the non-bonding electrons and is polar on the nitrogen, are also really good ligands. Now, the number of ligands that are attached was referred to as the coordination number, and that coordination number is really the number of atoms directly attached to the central metal. So, for example, cobalt with 6 waters around it would have a coordination number of 6. The cobalt, as we just saw there, would have a coordination number of 4 because it has basically 4 atoms directly attached. Now, sometimes people mess up on coordination number because they think it's always this number here, and it's not the case. These ligands, as we'll talk about in a later chapter, are sometimes referred to as being monodentate, which basically means they attach in one place per molecule. So for every one of those molecules, you basically get one attachment point. Same thing with the water. The water is going to attach through the oxygen, so to the metal. So you get basically just this one attachment point for each of those waters. But there are ligands that can attach in multiple places. For example, our C2O4, a little oxalate action here. So for every oxalate, for example, if you have a metal, it's able to attach through each of the oxygens in oxalate, the single bonded oxygens. And that means that if you had something like, say, a cobalt with oxalate, and we had 2 of them, for example, and I'll just say -2 overall. What would happen is the coordination number here would actually be 4 and not 2, and that is because basically our cobalt would attach there, and then we would have a second oxalate molecule. Won't draw all the electrons, but that could attach here and here. So from that oxalate molecule, there's 2 attachment points. From the second oxalate molecule, there are 2 more, and that's what gives us a coordination number 4. Something like oxalate is known as being bidentate, which means for every one molecule, basically you get 2 attachment points. And there's some that you could even have like 6 attachment points and so forth. So it does depend on the ligand. It won't always be the number on the bottom unless it is a monodentate and it just attaches in one place. It can have a different coordination number. And we'll get more into that in a later chapter as well. But so let's talk a little bit about KF type of values and problems and how we work these problems, which is a little bit different than how we work some of the other problems. And it is sort of the basis based on the value that we see for KF values. Typically speaking, KF values are really large values. So if you remember, our KSP values are usually really small values, but our KF values are actually really large values. And because they're really large values, that means that, you know, pretty much they're all going to the right-hand side. They're all going towards the product side. So if we have this problem here where we took 0.2 moles of copper 2 sulfate is mixed with a liter of 1.2 molar ammonia, what is the concentration of the copper 2 ion at equilibrium? For this particular example, and not always the case, we're just going to assume that everyone is a total volume of 1 liter. And again, not always the case. So we'll just got to keep the numbers the same here. So when we do these sort of ICE tables here to solve these problems, we do want to use our KF. So our KF in this case would be our concentration of our product over our reactant. And once again, we want to make sure for our NH3 in this particular case, we do take it to the 4th. Now we want the concentration of everybody. So the copper concentration, which would come from this guy, will be 0.2 molar. Again, just assuming we have 1 liter of it. So 0.2 divided by 1 would keep us at 0.2. So initially here we would have 0.2 molar. For our ammonia, again, we're just going to keep it at 1 liter. So we'll end up with 1.2 molar for that one. And we would have 0 here. So a difference that we do in this type of problem that's a little different than what we do in some of the other problems is because of the K value being so large in these type of problems, we assume that pretty much this reaction is going to head to the right-hand side and that all of the metal ends up in the complex ion. So that is basically the first assumption that we make when we do these type of problems, that because of such a large value of K, pretty much that metal is going to end up in that complex ion. Everybody's going to head to the right-hand side. So what we know in this case is what the change should be. The change should be the amount of copper. So we're going to do minus 0.2. We're going to do minus, we still need to take the coefficient. So this would be like minus 4x, but this is going to be minus 4 times 0.2 since we already know what x is going to be. And this will be plus 0.2. Any questions on that? So that's very similar to how we do with x's. This would be like minus x minus 4x, right? And plus x. The difference here is we kind of already know what x is, so we're just kind of putting it into our value there. Any questions on that there? So now we're going to carry down to the end here, which is going to give us 0 for this guy. We will end up with 1.2 minus 4 times 0.2. That's going to give us 0.4 molar, and this will give us 0.2 molar. All right. Now, at this point, we are looking for what is the copper 2 concentration at equilibrium. And based on our assumption, we see that the answer is 0, which means it's not much of a problem. So clearly 0 cannot be the answer in this case. So even though our first assumption is that pretty much all of that metal is going to be tied up in the complex ion because of the large value of K, this is still an equilibrium constant, which means even though almost 100% of it is going to go to the product side, there still should be some products that are going to go back the other way. So the second part of the assumption is even though almost all of it will be tied up in that complex ion, there will still be a very small amount of that metal that's still going to be free in the solution. And that amount should be a really small number. Yeah. So the second part of the assumption is it will come back a little bit, and we should only have a super small amount of that free metal still there. So what we're going to do in this case is we actually want to solve for how much of the metal is there. So we're going to now call the metal X in this case so that we can solve for it. And we're going to put this into our equilibrium expression, which means we would have 0.2 divided by X, which is really the copper concentration in this case, times our 0.4 that we still need to take to the fourth, and that's going to equal our 5.0 times 10 to the 13. We're going to solve for the copper concentration by basically swapping places with those two, and that would give us that the copper concentration would equal 0.2 divided by 5 times 10 to the 13 divided by 0.4 to the fourth. And if we do that, we will get 0.2 divided by 0.4 to the fourth divided by 5 to the 13th will give us a copper concentration here of 1.6 times 10 to the minus 13 molar. Yeah. Question on that there. My free copper concentration. Is that a lot of free copper floating around? That's pretty much nothing, right? It's like 0.012 zeros and a 1, right? So you basically have all the free copper in that complex ion, but a little bit of it will still break apart. So this does validate our assumption of pretty much it all went into the complex ion, and we still have just a smidge of it that will still be free, but it is definitely a very, very small amount. If you did this and you calculated the copper concentration, it was a really large number. Something went wrong because it should be a really small number. You know? Any questions on that there? Yeah. Why do I? That's just mathematically how you rearrange that. So you are taking. You got to multiply both sides by the copper, basically. Those will cancel, and then you got to divide by the 5 times 10 to the 13, which will put it back over here on the bottom. So it's basically just mathematically, that's how you rearrange that equation. And they basically end up swapping places. Yeah. Other questions? Yeah. Obviously, that gets away on that side. All right, why don't you try one here? Let's try this one. We want to know in this particular case, what is the concentration of silver? The concentration of AgS2O3 minus, AgS2033 minus, in a solution that's prepared by mixing 150 milliliters of 1 times 10 to the minus 3 silver nitrate with 200 milliliters of 5 molar sodium thiosulfate. We're not keeping the volume constant in this particular one, so you do need to take that into account. They didn't give you the overall reaction, but they did give you the stepwise dissociation of those ions coming on. So take a few minutes, see what you come up with. We're looking for really everybody's answer here. You may need to add it together to get the overall reaction. Might be a good idea. And see what you come up with here. Let's take a look, see how you're doing. So we're looking for everybody's concentration here. We do have the stepwise sort of formation. If we wanted to, we can add these together, and that will give us the overall sort of reaction that's taking place here, which is really our silver plus a couple of these S2O3 2 minuses, which would be our ligands in this case. We'll form this complex ion of S2O3 2 3 minus. We could even get the Kf value for this by once again multiplying these two together. And if we got that, you could use it. You might not even need to use it. We'll talk about that in just a second. Would be something like 2.9 times 10 to the 13. Any questions on that? What this overall reaction shows us is really we're putting these two guys together, and we have really sources of each of those things. The silver nitrate here going to be our source of our silver, and the sodium thiosulfate here will be our source of the S2O3 2 minus. So once again, we actually need the concentrations of these guys when they're mixed together. So we're going to mix them together. So we can use our M1 V1 equals M2 V2 and get the concentration of each of these. So our silver concentration should be 150 milliliters times the molarity, which is 1 times 10 to the minus 3. And the total volume here is we're taking 150 milliliters and adding 200 milliliters to it. And that's going to give us 350 milliliters as our total volume. And that is what we want to divide by here so we can have that total volume. Milliliters will cancel, so we'll take a 150 times 1 to the minus 3. divided by 350, going to get us, we'll call it 4.29 times 10 to the, looks like 1, 2, 3 minus 4 molar. We're going to do similar calculation here for our S2O3 2 minus. In this case, we have 200 milliliters of it times a concentration of 5 molar divided once again by our total volume of 350. The milliliters will cancel. That will give us 200 times 5 divided by a 350. Looks like a 286 on that there. All right. Any questions on that? All right, so I'm gonna do an ice table first off using my overall reaction, since I pretty much have the concentration of both of those things. So why not? So I can do it on this page. So my overall reaction again is the silver plus 2 of these guys going to my complex ion of AgS2O3 2. 3 minus. All right, so initially we had for our silver 4.29 times 10 to the minus 4. For our S2O3, we had 2.86 and a 0. Change here would be, again, our assumption that all of the metal is going to get used up. So our change would be our metal, 4.29 times 10 to the minus 4. This will be minus, once again, we do need to take that 2 into account. 2 times 4.29 times 10 to the minus 4. And this would be plus 4.29 times 10 to the minus 4. Coming here at equilibrium, we're going to have 0 of this guy. We will end up with 2.86 minus 2 times 4.29 to the minus 4. Still going to be really 2.86. And we will obviously end up with 4.29 times 10 to the minus 4. Any questions so far? Off of this first ice table, we actually got a couple of answers that we're looking for. We can see that we have the concentration of S2O3 2 minus is 2.86 molar. We also have the concentration of our final complex ion, which would be 4.29 times 10 to the minus 4 molar, right? So we basically have this guy's concentration. We also have this guy's concentration, which is the same as that guy's concentration. So we are looking for a couple of other things. We're looking for the silver concentration still. And we're also looking for sort of this intermediate sort of concentration as well. So there's a couple of things that you could do at this point, and a couple of ways you could solve it. So I'm going to solve it this way. I'm going to actually use the individual stepwise equilibriums to solve for what I'm looking for. And if I do that, I have enough information to go into the second step here. I have everything but the sort of intermediate that I'm looking for. So using the K2 reaction, not the overall reaction, but using the K2 reaction, our K2 would equal the concentration of our product here divided by our reactant, which would be this guy. Times the S2O3 2 minus. And that would equal 3.9 to the 4th. So putting in my numbers, which obviously, again, I have both of those numbers there, that would give me 4.29 times 10 to the minus 4 equals our concentration here that we're kind of looking for here on the bottom, times our 2.86. And again, that will equal, I'll just borrow that right there, 3.9 times 10 to the 4th. if you do the math, just like we did previously, these two guys basically will switch places. And we will end up with the concentration of this sort of intermediate equaling 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the fourth and our 2.86 in this case. And that will get us here 4.29 to the minus 4 divided by 3.9 to the fourth divided by 2.86. And depending on your calculator, you probably ran out of room with a bunch of zeros and a 4. If you put it in scientific notation, you got something like 3.8 times 10 to the minus 9. Or again, on a calculator, it may just have a bunch of zeros and a 4 at the end as it ran out of room. Any questions on that one there? Yeah. Why did I use the K2? Because after we did the overall table, the first size table, we had this guy's information and we had this guy's information, which by just using K2, it would allow us to get to this guy, which is one of the things we were looking for. So it just allowed you to kind of get that. I couldn't have gone to the first reaction because I only had this guy's information. So I had two unknowns of that one. So I couldn't use that one to kind of solve for silver or the other guy at that point. So that's why I went to K2 first. So, other questions? But now that I use K2, right, and I now have that sort of intermediate concentration, I now can go to the first reaction. And I can use the first reaction to actually find my silver concentration, because based on the calculation we just did, now I have this guy and I still have this guy, which will allow me to get to the silver concentration at this point. So that's what I'm going to do here. I'm going to use the K2 reaction to K1 reaction, I'm sorry, to get to silver. So K1 would equal, using our reaction there, for that first step would be this divided by our silver, which is what we're looking for, and our S2O3 2 minus. This would equal our K1, which is 7.4 to the 8. Putting our values in, again, we just solved for it, which would be 3.8 times 10 to the minus 9. Divided by our silver concentration, which is what we're looking for, and it is still 2.86 for our S2O3. Once again, mathematically, they're going to just switch places, and that would get us a silver concentration that equals 3.8 times 10 to the minus 9 divided by 7.4 times 10 to the 8. And 2.86. And if I do that, 3.8 to the minus 9 divided by 7.4 to the 8 divided by 2.86, going to give me 1.8 to the minus 18, which would be our silver concentration. And based on our assumption, right, our silver concentration should be a large number or a small number. Should be a small number, and that would definitely qualify as a small number, right? Question on that. So in this case, if you are given sort of the steps, you can use each step, because each step is an equilibrium, which means if you have equilibrium concentrations, you could go into it. Now, to show you sort of an alternative path that would also get you there is if we use our results of the first ice table. I'll do it right here. Try to squeeze it right there. If we use the results of our first ice table and the K value that we got for the overall reaction, which was 7.4 to the 8 times 3.9 to the fourth, remember that this guy's K value was 2.9 times 10 to the 13. We could have used this table and solve for silver just like we did in the first problem. So using the overall K value. So if we did that, we would have 2.9 times 10 to the 13 would equal our 4.29 times divided by our silver concentration and our 2.86 that we do need to square because we're using this equation here. And again, if we swap places with these two guys, our silver concentration would be 4.29 to the minus divided by 19 8 to 1% to the minus molar, which is exactly what we got using the individual steps. So you could still use the overall reaction and the overall K value, get the silver concentration. At that point, you would have some options as to where you could go next. You would at that point maybe have both of those. You could use K1 to get to the product. You could also then obviously use K2 to get there like we did as well. So you could have used the overall and then use the silver in some of the other steps and got it as well. Any questions on that? Okay, so again, stepwise formation here, still equilibrium constants. So you can still calculate what you need as long as you have some equilibrium concentrations. The reason we need to use everybody here is because of the question. It was asking basically for everybody's concentration. If it just wanted silver's concentration, probably the easiest thing to done might have been this step right here using the overall reaction. Yeah. All right, let's take a look at one last one here to wrap this up. In this case, we want to look for the ability of silver chloride in 1 molar ammonia. So actually have two steps here. We have the silver chloride breaking apart into silver chloride ion, and we have a KSP for that like we've seen earlier. 1 point silver plus the ammonia. Like value. If I add these reactions together, in this case, the silver is actually going to cancel out, and I will be left with silver chloride plus some ammonia will make this complex ion where the silver gets attached to the ammonia and some chloride. Now, since I added these reactions together, even though these are two different types of Ks, KSP and KF, can I multiply them together? The answer is yes. They're all still equilibrium constants. Doesn't really matter what the little guy says. So we can multiply these guys together to get our overall K value, which is going to be in this case, again, by multiplying those guys together, 2.4 times 10 to the minus 3 there, if I punched it in right. All right. So in this particular problem, we're actually looking for molar solubility, which means this reaction is really more of a KSP type problem like we've done before. So that is what we're going to do. We're going to do really a KSP type of reaction. And I'm just going to flip the page here and do it over here. So again, adding these together gives us our silver chloride plus our 2NH3 and our complex ion here. And our chloride. And again, our K was 2.4 times 10 to the minus 3. In this case, the only thing that was given to us was we got 1 molar ammonia, basically. So we're going to do a 0 and a 0. Since this is more of a solubility type problem, so this is going to be minus 2s, right? Because we do have the coefficient there. This will be plus s and plus s. A little bit different than some of them. We actually do have some stuff here on the left-hand side of the arrow. We are going to get to equilibrium here, and we will have 1 minus 2s, s, and s in this case. And we're not writing anything on the silver chloride because it is a solid, right? We'll go into our K expression, which for our overall reaction would be our products times all our both products and divided by our reactants, which again, here we do need to square because of that too. And that will equal our 2.4 times 10 to the minus 3. Putting in our values here, that's going to give us s squared up on top, 1.0 minus 2s squared will equal that 2.4 to the minus 3. I want to solve this for s. This is a perfect square, yes. So you can do a big square root on both sides would be probably the best move. And the thing that I forget to do most of the time is actually do the square root there. So I'm going to do the square root of 2.4 to the minus 3. And that's going to give us 4. We'll call it 9 times 10 to the minus 2 equals s over 1 minus 2s. We're going to multiply this to the other side, and that will give us 4.90 times 10 to the minus 2 minus 0.9 to the minus 2 times 2 will give us 9.8 times 10 to the minus 2s equals s. We're going to bring the s to the same side, so we're going to add it back over there. So that's basically 1 plus 9.8 to the minus 2. And that is going to give us 4.90 times 10 to the minus 2 is equal to 1.098 s. Lastly, we're going to divide this to the other side, and that will get us an S of we'll call it 5 times 10 to the minus 2 molar as our molar solubility here. Question on that there. So how does this compare to the solubility of silver chloride in water? We earlier calculated, I believe, the molar solubility of silver chloride in water. Silver chloride in water, molar solubility is 1.3 times 10 to the minus 5 molar. And if we want real kind of numbers to help us visualize what's going on here, we have a molar mass of 143.35 grams per mole times 1.3 to the minus 5. If you remember, the solubility of silver chloride in water was about 0.002 grams per liter. If we also multiply this by the molar mass of silver chloride, this will tell us the solubility of silver chloride in ammonia, which is what we did in this problem, which forms the complex ion. The solubility here is 6.45 grams per liter. Yeah. Which one is it more soluble in, water or ammonia? It is way more soluble in ammonia, right? You could get like over 6 grams of it versus 0.002 grams in 1,000 milliliters, right? Much more soluble in the ammonia, and that is because that's a good ligand, and that is why the formation of a complex ion is favored and why the Ka values are really large values. When a good ligand comes across a metal, pretty much they want to come together. This is actually how you would, since again we don't really do these experiments anymore, but you would have a solid of silver chloride. You could add ammonia to it, and that ammonia will be able to rip the silver basically from the chloride and make this complex ion, which is floating around in the solution. And then you could actually add some acid to it, which will deprotonate the solution and allow the silver and the chloride to come back, and you would see this solid come back together. So the formation of a complex ion is always sort of favored because of the large K value that we have. Do you have a question? on the right here. What? 1.3 times 10 to the negative 5 molar. Are we talking about this here? Yeah, that's 1.3 times 10 to the minus 5 molar. Yeah, that was the molar solubility of silver chloride in water, yeah. Which is obviously a lot less than it is here in ammonia. So those complex ion formation is definitely favored, which is why, again, we do see those really large values for K. And that's really why we make those assumptions when we do these calculations, that pretty much all the metal, if there's a good ligand, will want to come together and make that complex ion. It's really favored over most things because of the really strong attraction that there is. And as you can see, the very big difference in solubility between it and water, and the solubility of it in that complex ion sort of formation makes it really soluble. Any questions on that there? And here's a table from your book of some KF values. And as you can see, if you kind of scan through these, they're pretty large values, which means, again, we will make those assumptions when we do these type of problems. Any questions on KFs? That wraps up chapter 15.